All right, geometry. Here's your notes for the quadratics unit. We're just going to call them quad 1, quad 2, quad 3, quad 4, quad 5. Quad 1, just talking about quadratic functions. And I know some people, when you see the word quad, you're thinking 4. It has nothing to do with the number 4. This is what a quadratic function looks like. If you have your notes handout, write that in there. It's y equals ax squared plus bx plus c. Quadratic coming from the squared here. If I didn't have that, recognize maybe that this would be a linear function, bx plus c. A lot of times we call it mx plus b, but regardless of the coefficient, a quadratic will have a power of 2 on it. Instead of a linear function making a line, a quadratic function makes a parabola. Write that down, parabola, and maybe even say it out loud to yourself a couple times so that you call it a parabola. Dun 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 dun, dun parabola. Dun 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 dun, parabola. Say it right. This is the most basic parabola. Y equals x squared. It doesn't have a coefficient in front of it. It doesn't have any more variables or constants after it. If you just type in or graph y equals x squared, you get a parabola that looks like this. Nice, smooth, rounded curve, U-shaped. And we're going to change the look of it a little bit. Is it going to get taller or shorter, or is it going to move around, or is it going to be upside down? But we'll get to that. A couple more vocabulary to go with quadratic functions and parabola. You need to know what a vertex is. So in looking at this diagram right here, the vertex, write that word, vertex. In this particular picture, it's at 0, 0. If you look down here, this green dot that I put on there is at 0, 0. Vertex is the place on the parabola that changes directions. It was going down, 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 down. It hits the vertex, shoots right back up. In this case, it's the lowest point of the graph. Now I'm going to have you write over here, because the vertex isn't always at 0, 0, I'm going to have you write x, comma, y, to remind yourself that the vertex is always a coordinate. It's just a single point on the graph, and it's the point where the graph changes direction. And then we have the purple line, if you can see the purple on mine, write it on yours, axis of symmetry. This axis of symmetry, it is a dotted line, as you see here, and the reason why it's dotted is because it doesn't actually exist. For those of you that do not know this, the North Pole, South Pole on the planet Earth, there's not actually a pole that runs all the way from the north of the Earth to the bottom or south of the Earth. We say that the Earth spins on its axis, but there's not really a pole that goes all the way through it. It's imaginary, just like this. This axis is imaginary. It splits it right smack down the middle of the parabola. Axis, why is it called symmetry? Symmetry, you'll get a lot more of that, or you have gotten a lot of that in geometry. It means that one half is exactly the same as the other half. If we folded this on its axis of symmetry, you'd get the same. Or if you put a mirror on the axis of symmetry, you would see both sides. It passes through the vertex, and it is a vertical line. Because it's a vertical line, you have to answer your question as where is the axis of symmetry as x equals. In this case, it would be x equals 0. You can't just put a 0, because just putting a 0, we don't know which one is a 0. By saying x equals 0, it means all of the points on the axis of symmetry are at 0. I could call this one is at 0, negative 1, 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. If I wrote all those points as the axis of symmetry, all of the x values would be 0 no matter what. So you say all of the x's equal 0. And it will just so happen, because it passes through the vertex, that question mark, that x value, will always match the x coordinate of the vertex. The vertex and the axis of symmetry have to match. It has to go right through. So let's just practice a couple of those. What if you were given a graph like this? It asked for the vertex and it asked for the axis of symmetry. The vertex you would find as the point that changed directions, count it over on your graph, 2 spaces to the right, but 0 spaces up. Axis of symmetry, you can draw it if you'd like to. You don't have to unless they ask you to. The axis of symmetry is x equals 2. All the values on that vertical line are 2, and the vertex x-coordinate will match. Try the next one. Got the red graph. Where is the vertex and the axis of symmetry? Vertex over 1, 2, 3, and up 1. Over 3, up 1. Where is its axis of symmetry? At x equals 3. And the last one looks a little different. It is still a parabola. A parabola doesn't have to fit perfectly and be U-shaped facing straight up. It can be down. The vertex is still the place where it changes direction. Where is it changing direction? Right here, now it's at the very maximum of the parabola. The maximum being up there. So it's going left 1, up 2. If you count back from the origin, left 1, up 2. Axis of symmetry, x equals -1. So that's the vocab. Now what we're going to do from there is actually make the graphs of the parabolas, and we're going back to old school days of the T-chart. As you see on my T-chart over there, I've got the numbers -2, -1, 0, 1, and 2. Believe it or not, for the rest of your life, if you were asked to graph a graph, you would be able to do it by making a T-chart. I don't care what this equation said. If you use a T-chart, you'll be able to make part of a graph. Okay, in this case, why do I pick those numbers? Simple. You pick the 0 because you got to know what's happening in the center of your graph. Got to know what's going on with your graph right smack at the origin in the middle. And then you pick a couple of smaller numbers, 1 and 2. You might say 5 is my favorite number, but 5 squared is 25. You don't want to graph over 5 and up 25. You can't even reach that. So you want to use nice small numbers, especially when you're working with a squared. And of course, you also have to pick negative numbers. If you only picked the positive numbers, you would never know what a parabola actually looked like. You have to pick negative numbers to know what's happening on the other side. So you're going to type this into a calculator if needed. If not needed, you don't need the calculator. But if you use a calculator, you've got to use parentheses. Try it if you don't trust me. If you type in -2 squared in parentheses, you get 4. If you type in -2 squared without parentheses, it'll give you -4, which is incorrect. You want to square the negative and the 2. So we get -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. This happens often, the little pattern that you see. Not always, but often. Graph it by going left 2, up 4, left 1, up 1, 0, 0, right 1, up 1, and right 2, up 4. And don't play dot to dot here and make some rigid marks on it. Make a nice smooth parabola, and also you're not just starting at this dot. We started there, but the parabola continues. So start above it, make a nice smooth rounded curve, and come back up the other side. This graph is called the parent graph, or parent function, because it's the most basic of all the parabolas, all the quadratics. That's the parent function. There was no coefficient in the front. There was nothing added or subtracted to it in the back. So that is the most simple basic graph. So what happens if we take that same graph, same equation, but multiply it by 3? As you may know, anytime you multiply by a whole number, something gets bigger. Well, let's see if our graph gets bigger. Now you're plugging in 3 times -2 in parentheses squared, or you can do it in your head if you know that 2 squared is 4. 4 times 3 is 12. 3 times -1 squared is 3. 3 times 0 squared is 0. 3 times 1 squared, 3 times 2 squared is 12. So now when we try to graph this, we're shooting way off the graph. Left 2, up 12. It's way the heck up there. We may not even have to use that one. Left 1, up 3, 0, 0, 1, 3, and again 2, 12. We don't have to use those points at the top, but you do have to know you're not going to just make a little tiny parabola right here. You're going to go off the graph. But when you go off the graph, you cannot go past the number 2 or -2, because you know that 9 or however tall your graph is, you got to keep going. So we're going to start a little bit inside the 2 and negative 2 and swoop it back up past that way. So it's going to ask, if you compare that to y equals x squared, look at our y equals x squared graph. Our y equals x squared graph, how did 3x squared change it? It looks like it's skinnier. Like you might want to say, oh, it's definitely smaller, it's skinnier. That's not how we represent this. You know that multiplying by a whole number will make anything bigger. Okay? Anything that's not a decimal or a fraction. We're going to make it bigger. We're multiplying by 3. And it's asking us to compare the y values. Here's the y values. What happened when this was at 1, 1? It went from 1, 1 to 1, 3. This point 1 went up 3 times as big. So did negative 1. Went up 3 times as big. 2 was supposed to be over 2 up 4. But instead it went over 2 up 12, which was way up there. So in describing this graph, how does it compare? It got taller. You don't say that it's skinnier or that it's narrower. The look of it makes it look narrower. But at the same time, I mean, if I grew about 7 inches but never gained any weight, wouldn't I look skinnier? Okay, but technically I didn't lose any weight and get smaller. If I grew 7 inches and kept my same weight, I would look skinnier. That's what's happening to your parabola. So how does it compare to y equals x squared? It's taller. You could even say it's 3 times taller than y equals x squared. All right, let's try the next one. We've got y equals 1/4 x squared. So now technically, instead of multiplying, we're dividing. Because if you think of it, a fourth or divided by 4, it means the same thing. So we're going to multiply it by a fourth, which is the same as dividing by 4. Look at what I did to my t-chart. I changed the numbers over here. Knowing that I had a denominator of 4, I didn't want to have any decimals here. Could you leave it as -2, -1, 0, 1, and 2? Sure, if you don't mind graphing decimals on your graph. But using the 4s and multiples of 4s, it'll help not have any decimals to graph. So we're going to go with 1/4 times parentheses -4 squared. Type that into your calculator, you'll get a positive 4. 1/4 times -2 squared, you'll get 1. 1/4 times 0 squared is 0, and then a 1 and a 4 again. So far, our pattern has maintained 4, 1, 0, 1, 4. So we're going to go left 4, up 4, left 2, up 1, 0, 0, over 2, up 1, and over 4, up 4. And you will again be asked to make a nice smooth parabola through the dots. Let it keep going past. And the question is, how does that compare? You got to take what you just learned from the last graph. The last graph we said it got taller because it stretched out taller. Well, what did this one do? This one was supposed to be at 1, 1. Let me move it up where it is. 1, 1, but it went from 1 down to a quarter. It was supposed to be at 2, 4, but instead of being at 2, 4, it's only at 2, 1. So this graph got shorter. When you shorten the graph, it of course looks much wider. What happened to it? It is shorter. And you could say 4 times shorter than it was before. Every point that it was now becomes divided by 4. Okay, so now you know what the parent function looks like. You know what happens if you multiply by a number, it stretches it out. You know if you divide by a number or use a fraction, it shortens it. But what happens if you add to it? So some would say, well, if you add to it, it'll also get bigger. Not necessarily. Let's try x squared plus 5. You're plugging in -2, -1, 0, 1, and 2 again. I keep giving you these numbers, but if I don't give them to you, you got to use the same ones. -2 squared plus 5, use your -2 in parentheses, comes out to be 9. -1 squared plus 5 is 6. 0 plus 5 is not 0. I wouldn't believe how many kids after all this just put 0, 0. It's 0 plus 5 is 5, 1 plus 5 is 6, and 2 plus 5, or 2 squared plus 5 is 9. Again, same pattern, and I'll explain why. Negative 2 up 9, that's only off the graph by 1, we could use that. Negative 1 up 6, negative 0 up 5, not negative 0, 0 up 5, over 1 up 6, and over 2 up 9. So we have our graph, nice smooth parabola, do your best. And it's going to ask us, how does that graph compare to y equals x squared again? So I'll put that up there. And you might look at that and be like, oh, it got smaller. Why did it get smaller if it says plus 5? It looks like a smaller graph. Well, that's an optical illusion. It is not a smaller graph. It just looks smaller because of where it's placed. Watch this. Ooh. I'm gonna hook that back together so that it moves together. Maybe. Take my vertex with it. There we go. If I move that 1, 2, 3, 4, 5 spaces, it's exactly the same graph. What does the plus 5 do to my parent function? It didn't change the shape of it at all. All it did was move it up 5. Why didn't it change the shape of it, make it taller or shorter? Because this coefficient right here wasn't a number other than 1. When we had it 3, it got taller. When we had it 1/4, it got shorter. But that one stayed. So the shape didn't change, just the location. So now we're going to subtract 2, but with parentheses this time. I don't know if you can even predict what's going to happen to this. No numbers over here on the T-chart, so let's go with negative 2, negative 1, 0, 1, and 2, because there's no fraction up there, so we can just go with those. But now, carefully, when you put it in your calculator, it's going to be negative 2, subtract 2 squared. Negative 2, subtract 2 squared. Should give you 16. Then negative 1 subtract 2 squared is 9. 0 subtract 2 squared is 4. And you might be tempted to just go, oh, 16, 9, 4, 9, 16. But 1 minus 2 squared is 1. 2 minus 2 squared is 0. We have a problem. Let's start graphing this and see what happens. Of course we can't graph negative 2, 16. It's way too high. We can graph negative 1, 9. We can graph 0, 4. We can graph 1, 1. And 2, 0. It looks like maybe it's about to turn. We can't stop there. We know that we need a parabola. And if we need a parabola, we're going to have to keep going until it goes back up. So let's try a 3. 3 minus 2 squared. Oh, I see it. We're going back up. Over 3 up 1. Let's try a 4. 4 minus 2 squared is 4. So we're going over 4 up 4. And you could do a 5, which will come out to a 9. And now you see your parabola. You've got to have at least 5 points. That was not a very good curve. Let's try that again. You've got to have at least 5 points to see about where your parabola is. So what happened if we compare this one to y equals x squared? This was y equals x squared. Y equals x minus 2, believe it or not, it moves 2 spaces to the right instead of to the left. You're thinking that's a minus and it should move left, but it does just the opposite. It's going to move right 2 spaces. When we did the plus 5, where was that? It went up 5, just like you said, plus 5. But now we're doing the minus 2, and it actually went to the right 2 spaces. One more. How about y equals negative x squared? We've got y equals negative x squared. We're going to try negative 2, negative 1, 0, 1, and 2. It didn't work for us last time, but we'll try it. And you'll get the opposite of negative 2 squared. That's how you have to write that in your calculator. The opposite of negative 2 squared, which will end up being negative 4. The opposite of negative 1 squared is negative 1. 0 squared is 0. Please don't put negative 0. 1 squared, the opposite of 1 squared is negative 1. The opposite of 2 squared is negative 4. So when we graph this, we're going left 2 down 4, left 1 down 1, 0, 0, over 1 down 1, and over 2 down 4. Exact same parabola, but well, how is it different from the original? Please don't use the term upside down. That's not very mathematical. How is it compared to y equals x squared? It reflected down compared to the original. So now you know that anytime you have a minus, it's going to move down, or reflect down, I should say. If you have a number in the parentheses, it's going to move either left or right. If you have a number outside of x squared, it's going to move either up or down, depending if it's positive or negative. If you have a fraction or a decimal in front of x squared, it's going to get shorter. And if you multiply it by a whole number, it's going to get taller. So from there, you're going to figure out all the different types of equations and shapes of graphs. Good luck.